So welcome to the third video of solved examples on indexing. In this video, we will solve the opposite problem to that of what we saw in the previous video. So in this video, the directions are given and we have been asked to find out the indices of those given directions. The four directions are given in a single unit cell: direction A, direction B, direction C, and direction D. And we want to find out the indices of all the four directions. Later on in this video, we will also solve the same exercise on planes. Okay, so let us find out the direction of each. Let us find out the indices of each one of them. Direction A particularly, it starts from here, from this, and then it goes over the top plane. It completely inside the top plane and ends at that corner of the unit cell. Then direction B originates from the origin of the coordinate system, and it ends on this plane. So direction B ends on this plane, such that the distance of this tip from x-axis and from y-axis is half, right? So the distances of this half and half correspond to the distances from the edges of that square face. So from that edge of the square face, half, and from vertical edge of the square face, half. So that is the meaning of half and half. Then let me clean this. Okay. Then direction C. So direction C is here, and it originates from the middle or the center of this edge of the unit cell, and it terminates at this corner of this unit cell. Okay. Finally, direction D originates from this center of this edge, bottom edge of this unit cell, and it terminates at the center of this edge of the unit cell. Okay. So although half is not given here, this should be actually half. Okay. So let us solve them one by one. Let us find out the indices one by one. So direction A is shown individually here. Other directions are not shown on this slide. And we will use the same four-step procedure for finding out the indices of this direction. Now, this is the tail of direction A, and here is the tip of direction A. The step 1 of the procedure says that the tail of the direction must lie at the origin. Okay. We have two choices: either we shift the origin from this position to that position, and then we have a new set of coordinate axes here, which are parallel to the original x, y, and z. So that is one choice. Or we translate the direction such that its tail passes through origin. So if I let me do that. So if I translate this tail of the direction at this point at the origin, then the tip of this direction gets translated at that corner. Okay, so after translating, this will become direction A. Okay? So I think this is an easier alternative as compared to translating the origin. So we will use this alternative. We will translate the given direction. Okay, so let me erase this. So we don't want to translate the coordinate system, but we will translate the direction itself. For translating direction, so I will first translate the tail of the direction at this at the origin of the coordinate system, and then actually this will happen at the same time. I'm just telling you tip and tail differently for the clarity. So if you don't understand, uh, let me tell you this way, that if I translate this direction A such that its tail lies at the origin, so let me use another color because I'm using green color for the direction. So if we translate the direction such that the tail of the direction lies at the origin, then its tip will lie at that corner. So at this corner, tip will lie at that corner. And hence, after translating the direction A such that its tail lies at the origin, the direction A looks like this. Okay, so this is the translated direction A. So you don't know on this. So this is the direction A. And now we want to find out the indices of this direction. So we can now move on to step 2 because we have already completed step 1, which says that ensure that the direction the tail of the direction lies at the origin, or the direction originates from the origin of the coordinate system. Then step 2 is projection. So now we project the tip of the direction on x, y and z axis. So let me project it on x axis. So you can also do this with me. You can pause the video and draw the coordinate system, okay, there, and then you can also follow the same steps. So that is the projection on x-axis. And so for drawing projection on x-axis, you must understand that we must draw a line parallel to y-axis. Okay, so this line here which I have drawn, which is a projection on x-axis, or for finding out projection on x-axis, I have drawn a line parallel to y-axis. Okay, so you must understand this. Then now we find out the projection on y-axis, and to find out the projection on y-axis, I must draw a line which is parallel to x-axis, starting from the tip of the direction. So this is the projection on y-axis. Then we find out the projection length. In step 2, we want to find out the projection length on x-axis and projection length on y-axis. Okay, sorry, that is not the projection length on y-axis. The projection length on y-axis is this. Okay, now as we can see that this projection length on x-axis is equals to the lattice parameter. So if a is the lattice parameter along x-axis, then this projection equals to a, or minus a because it is on the negative side of the x-axis. Similarly, if the lattice parameter along y-axis is b, then this projection length is equals to b. Now we want to represent these projection lengths in terms of the lattice parameters. So minus a, sorry, so minus a by a, b by b. Now, as this direction lies on the xy plane, the projection on z-axis will be 0. So if I try to draw the projection on z-axis, for drawing projection on z-axis, I must draw a line parallel to xy plane. So I will come at the origin, and hence this projection length is 0. And if c is the lattice parameter along z-axis, then 0 divided by c. Then we drop the lattice parameter. So we have minus 1, 1, and 0. Okay, so then step 3, if there are any uh, fractions, then we multiply all the indices by a common factor, but there are no fractions here, and that's why there is no need to multiply them by a common factor. And finally, step 4 is enclosure inside the square bracket. So I'm enclosing the indices within a square bracket. So 1, 1, 0. So we don't write minus here. For negative index, we give a bar. So 1 bar, 1, 0. So those are the indices of this direction. 1 bar, 1, 0. Then direction B. So direction B is shown here, and it basically originates from the origin, and its tip lies on this face, right face of that unit cell, and the distance of the tip is half uh, from the bottom edge. So that means vertically that is half. So this is half of the vertical distance. Sorry, not half. So it's half of the length of this vertical line, and it is also half of the length of that horizontal line. So this from the vertical line it is half. So that's why the half and half indicated in the diagram on first slide. Okay. So we want to find out the indices of this direction B, and so I'm keeping those two values there. So to find out the indices, we will have to first draw the projections on x, y, and z axis. Okay. So I'm directly drawing the projection on z axis first, which is parallel to xy plane. So you will have to visualize this because we cannot directly show a line which is exactly parallel to xy plane, but this needs a little imagination. So I'm drawing a line which is parallel to xy plane. So that is where that line or projector intersects z axis. To find out the projections on x and y axis, first we need to project that tip down to xy plane. So I am projecting down to xy plane. You can also do this along with me. And from this point, now I will draw projections on x and y axis. So this projection comes out to be at half of that length. And now from this point, I will draw the projections on x and y axis. So this is the projector on x axis parallel to y axis. Okay. And finally to okay. So those are the projections on x, y, and z axis. So this is the projection on x axis. This is the projection on y axis, and that is the projection on z axis. Now we have to find out the length of those projections or distance of those projections from origin. So from origin, this is the distance of this projection on x axis. This is the length of projection on y axis, and this is the length of projection on z axis. Okay. So if the parameters, lattice parameters are a, b, and c, then we can write the projection lengths as fractions with lattice parameters. So a on x-axis, the projection length is half of a. So a by 2 divided by the lattice parameter a. It's on the positive side of x-axis. Then on y-axis, the projection length is equals to the lattice parameter b, and b divided by b. And on z-axis, this is c by 2. The projection length is c by 2. On y-axis it was b, and on x-axis a by 2. Okay. So for z-axis, c by 2 divided by c. Okay. All positive. Then we calculate this ratio. So we get half. B by b is 1. C by 2 by c is half. Okay. Step 3, multiply. If fractions are there, by the common factor. So as both the denominators are 2, then we multiply this by 2. So we get half into 2 is 1, 1 into 2 is 2, half into 2 is 1, and finally enclosure into square brackets 1, 2, 1. Okay, so those are the indices of direction B. You can try finding out the indices of direction C, which is drawn here, and uh, your answer should be 0, 1 bar, 2 bar. You can pause the video right now and solve this, check your answer. If you have any difficulty, you can post your difficulty on Google Classroom. Similarly, for direction D, you should get answer, or you should get indices, or it should be a square bracket. You should get the indices as 1, 2 bar 1. Okay. So let us now find out the indices of some given planes. So in this single unit cell here, there are three planes given: plane A, plane B, and plane C, and we have been asked to find out the indices of those three planes. Okay. For reference, the distances are given for plane A. There are no distances given because all the three vertices of that plane lie at the corners. For plane B, uh, the intersection with y-axis is at 1/3 of the lattice parameters from the origin, or from z-axis, or xz plane actually. For plane C, the this edge of plane C lies or coincides with the edge of the unit cell, and uh, this corner or this edge ends at the middle of that face of the unit cell, and it intersects the vertical lines or the edges of the unit cell exactly at their centers. Okay, so that is for your reference. Now let us find out the indices of the planes one by one. So on this slide, only plane A is shown, and for the clarity, other two planes, plane B and plane C, are not shown here. So that is the plane A. Okay. And we want to find out the indices of this plane. Now, according to the procedure, the step 1 says that the given plane should not pass through origin or should not touch the origin. Okay, and as we can see here, the plane given plane A, or this vertex of given plane A, touches the origin or passes through the origin. Okay. So that's why we have two options. Either we can translate the plane. So I can draw a plane here in the adjacent unit cell. So supposing that there is an adjacent unit cell here, so I can shift the plane at that position. Okay, or I can translate the coordinate system. Okay, so I can translate the coordinate system in this direction, and I can establish the new origin. So this is the origin of the coordinate system, which I am shifting to this position such that the axes remain parallel. So that is the z dash axis parallel to z axis. Here is the origin. That is the x dash axis parallel to x axis, and that is y dash axis parallel to y axis. So we have two options. First option is shifting the given plane, and second option is shifting the coordinate system. Okay, so any one of them will do. So for now, I'm assuming I'm going with option 1. I'm shifting or translating the given plane to a new position, but I'm keeping the coordinate system as it is. Okay, so I'm not translating the coordinate system. So I'm not going with option 2. Okay, so I don't need a new coordinate system. So I'm shifting the plane. We are going with this option. And now, in this shifted or translated position, this plane does not pass through the origin. Okay, so as you can see, so roughly, uh, I should draw the unit cell for the reference. Okay, so this is how the unit cell, adjacent unit cell, looks like. Okay. Now we want to find out the intercepts on x, y, and z axis. So first is x-intercept. Now this plane intersects x-axis at this point, y-axis on the negative side at this point, and z-axis here. Okay, so now we can find out the projection length or the length of intercepts. So this is the length of intercept on x-axis, length of intercept on y-axis, and length of intercept on z-axis. And as you can see, all the intercepts are equal to the lattice parameters along the corresponding axis. So if A is the lattice parameter along x-axis, B is the lattice parameter along y-axis, and C is the lattice parameter along z-axis, then writing out the fractions, the projection length along x-axis is equals to A, projection length along y-axis is equals to minus B, and along z-axis is C, and hence the ratios are A by A minus B by B and C by C. Then this will be equal to 1 minus 1 and 1, and as there are no fractions, reductions are not necessary. Finally, we can directly enclose them 1, 1 bar, 1. So those are the indices of, sorry, we should not be enclosing in square brackets. Okay, so we are now indicating plane, and hence we should enclose them in curly brackets or parentheses, not curly brackets, round brackets or parentheses. Okay, so 1, 1 bar, 1. Now let us find out the indices of plane B. So that is the plane B, and this plane is parallel to xz plane, hence parallel to both x-axis and z-axis, and it intersects y-axis at this point, and the corresponding point on top plane is this, and that point is a distance 1/3 of h length from xz plane or origin. So if A is the lattice parameter along x-axis, B is the lattice parameter along y-axis, and C is the lattice parameter along z-axis, then we can indicate the length of projections along x, y, and z-axis in terms of lattice parameters. So let us find out the projections. So this projection length along y-axis is so this length is b by 3, and there are no projections on x and z axis because the plane is parallel to them. Hence I can write in terms of lattice parameters. If the plane is parallel to an axis, then the projection is infinite for that axis. So sorry, this should be infinity. by A, then B by 3 by lattice parameter along y-axis, and infinity on z-axis. As it is parallel to z-axis, we take the projection as infinity divided by C. So infinity by A is infinity, then B by 3 by B is 1 by 3, and infinity by C is infinity. The next step is reciprocal, so we take reciprocals of them. So 1 by infinity, 1 upon 3, and 1 upon infinity. So they come out to be 1 by infinity is 0, 1 upon 3 is 3, 1 upon infinity is 0, and then reduction. So as there are no fractions, there is no necessity of reduction, and finally we directly go to enclosure. Again, we have to use the round bracket or parenthesis to enclose them. So 0, 3, 0. So those are the indices for plane B. Similarly, you can try finding out the indices of plane C, and you should get the answer as 1, 0, 2 bar. Okay. If you have any doubts, feel free to post your doubts on Google Classroom. See you in the next video.